Am I audible? Hello? Hello, am I audible?
Yes, ma'am.
Okay, thank you.
Good evening.
Good evening. Yes. Welcome everyone for the week 8 like problem solving session of the NPTEL course and Introduction to Climate Dynamics, Variability and Monitoring. Just like our last lecture, we will today start from the atmospheric and the oceanic circulation. First, we will see how the atmospheric or circulation velocity gradient and the velocity directions, those were derived using physics criteria. So for deriving any of movement of any air volume, you have to consider first one thing. Consider a small parcel of air. Just put that small parcel of air in some location of the northern hemisphere or the southern hemisphere. So here in this picture you can see this air parcel has been put in the northern hemisphere where the phi is positive, and while in southern hemisphere you have to put the phi is a negative. All these equations were derived using this northern hemisphere kind of image, but while calculation you can put for the southern hemisphere phi negative. So any of the this air volume or the air parcel can move any of the direction. Now movement of this air parcel can be described by three independent coordinates. So first coordinates is along the k cap direction, or that direction is parallel to the radial direction of the earth, and other two directions are the I cap directions and the J cap directions. And this I cap direction is from the west to east. This direction is known as the zonal direction, and the zonal equations has been written for this direction I cap direction. And for the J cap direction, this J cap is from the south to north. This J cap is known as the meridional direction. When the considering the wind movement, you have to first write the momentum equations in the both the three coordinates, as these three coordinates, those equations are known as the zonal equation, meridional equation and the vertical equation. Here in this lecture, first started with this writing these equations in specific format. Now this air parcel feels different kind of forces. Any air parcel can feel four types of forces. One force is the first force is the Coriolis force, which arises due to the movement of the due to rotation of the earth. And the second type of force is the pressure gradient force, that is Fp, because the any air volume has its pressure, it exerts its pressure. And this gravitational force, because it is on the earth's uh, gravity bound. And another is the friction force, that is the force in between this air parcels themselves, and also this air parcel volume or the air parcel cylinder and the earth. Now this wind velocity vector, that is the bold V, can be written as the three independent component what we saw. First component is the I cap component, that is from the west to east. J cap component is the south to north, and this I cap is the to the your just top of this U, that is the along the radial direction of the earth, or K component. Now this equation you can consider this K is towards U, I is I and the J at the makes a plane kind of thing. You can consider this IJ plane and then consider this kind of figure. Now this Coriolis force has the two terms. You can see the first effect of the Coriolis force or the first effect of the Coriolis force arises from the conservation of angular momentum principle. So why this angular momentum is conserved? angular momentum is conserved because Earth's rotational velocity, that is omega, does not changing with the time. So angular velocity conservation gives some component of the Coriolis force, and another component of the Coriolis force comes because of the centrifugal force part, because you can see that this air parcel has been in the rotating frame. So for the net Coriolis force is the sum of the Coriolis force which arises for the angular momentum conservation plus the part which arises from the centrifugal force term. So Coriolis force can be written as the two Coriolis force can be written as the I, J and the K directions combination. So here you can see the Coriolis force has been written in this V I cap, if velocity of this wing parcel is V I cap plus U J cap plus W U V W, sorry, U V W in the directions of I, J, K, then this Coriolis force can be written by this equation where I cap has the contribution from W and V, J cap has contribution only from the U, uh, and also K cap has contribution only from the U. So the U is the component along which the Earth has been U is along the I cap component, and this Earth's velocity, or this, you can see the velocity of the Earth is also along this I cap component. So in the vertical direction, the gravitational magnitude is much larger than the Coriolis force. So the vertical component of the Coriolis force, that is U cos phi k cap, that can be neglected. Now further, in the Earth's atmosphere, the vertical components of the wind velocity is significantly smaller than the horizontal component. This W term contributes to very small in the Coriolis force. So in this approximation, you can neglect this k cap term, on the cos phi W is tends to 0. So here you remain 2m phi V sin phi I cap minus U sin phi j cap. So the net Coriolis force becomes this F Coriolis is equals to this formula 2m phi V I cap minus U j cap. Here also you can write 2 omega sin phi, this as a parameter F, which is known as the Coriolis parameter. Now other than this, so the main idea for this first two pages were to write the Coriolis force as the function of the two direction, that is I cap direction and the j cap direction. This k cap direction, this Coriolis force is neglected. But now also there is another, the second kind of force is the pressure gradient force. You know that the air or the water, these fluids move along the pressure gradient, that is from the high pressure region to the low pressure region. One can write the pressure gradient force to be the pressure gradient force per unit mass to be 1 by minus pressure gradient force per unit mass is equals to minus grad P by rho, this term. Now you can write this grad P with the three component, or dividing between three components I cap, j cap, k cap. So this equation from the grad P, this equation comes directly. Now in the vertical direction, any of the air parcel or air column, we can say, that maintains the hydrostatic balance. So this hydrostatic balance is when this gravity balances this pressure gradient force in the vertical direction. So for the vertical direction also, there you can write gravity as also a function of the gravitational potential of a body. So one can rewrite this pressure gradient force per unit mass as the function of the grad phi also. It has been shown here that if we draw a state of the constant pressure surfaces from the sea level to the upward, as seen in this figure, here is the 1013 hectopascal pascal. Next is 900 hectopascal, 800 hectopascal, 700 hectopascal, and this pressure is falling as we are going up in the vertical direction or the z direction. Here the derivatives of the geopotential are needed to be taken along the constant pressure surface xy direction respectively. So the pressure gradient force is given by the slope of the geopotentials in x and y direction along a constant pressure surface. This means that the steep slopes of the constant pressure surfaces as one moves from the x or y direction as a result of the large pressure gradient force in the zonal and the meridional direction. And also you can also you can write the balance between Coriolis force and the pressure gradient force in the condition where from the at the large spatial cases spatial scales, that is about greater than 100 kilometer and away from the surface, so that the frictional effects are small, and far from the equator where Coriolis effects are weak, the only horizontal forces that is important is that for driving the air at the horizontal pressure gradient force, that is the 1 by rho del p del x, this component, and del p del y 1 by rho, this component. So this two components when then balances the the Coriolis force, and this balance is known as the geostropic balance. This geostropic balance also hold for the oceanic circulation as well the atmospheric circulation, and this geostropic balance will also hold for oceanic circulation below the wind agitated mixture layer and far from the coast and the equator. Now if you just write this 1 by rho del p del x for the your vertical the I component and the j component, that is f v I cap, and this f u minus f u j cap component from your Coriolis force, you would get one characteristics Vg for which gives the Vg or the meridional component of the geostropic velocity, and also you would get another Ug that is known as the zonal component of the geostropic velocity. You can write bold Vg, that is the geostropic component of the geostropic total velocity, which is in the surface between I cap and the j cap direction. Or the geostropic velocity vector, that is can be written as a function of the gradient of p. You can see here just by writing this, just by summing this equation. Also there is a phi dependence, so you can say that this geostropic velocity vector or the planar geostropic velocity is related to the pressure gradient by one equation, and by another equation it is also related to the gravitational potential or phi. This geostropic velocity is seen perpendicular to the plane containing the pressure gradient or the geospatial gradient vector and the vertical direction. So this equation dictates that the wind will be tangential to the pressure gradient line, and hence it will move around the circular motion around the low pressure. So you can consider that in this figure, suppose there is a low pressure zone here. Here is a low pressure zone and here is a high pressure zone. So you can say the pressure gradient is which direction? So pressure gradient is along this I cap direction or the j cap direction in this plane. So if you just write, if you just want to view this direction of this geostropic velocity vector, then you have to k cap cross k cap cross grad p. Grad p is I cap direction. So you can get a counterclockwise sense of rotation. By this means you can see the how the cyclones and the anticyclones move. Here you have to consider both f value and this grad p's direction in the both two in the both two hemisphere. So by this equation it is seen that the cyclones and the anticyclones rotate in the different directions in the southern and the northern hemisphere. Also you can rewrite this 7.23 and 7.24 by using the ideal gas law, that is the pressure is equals to rho kBt, and by writing that you will find that the how this temperature gradient, how the del Vg, how the Vg varies as the temperature as the pressure gradient and the temperature gradient. So here it's seen that the temperature gradients are taken to be along the P constant surface. This equation shows that the differential change in the geostropic velocity vector with the change in the pressure along the vertical direction at a given altitude is equal to the temperature gradient of the constant pressure surface in the horizontal direction at this that altitude. In the vector form, these two components can be added and this equation is called the thermal wind equation, where the change of geostropic velocity vector with the log vertical pressure is written as a vertical pressure temperature gradient with pressure, and the cross term k cap term and the f or the 2 phi omega sin phi terms. Yes.
Excel me,
Yes.
how where log p comes there?
Yes, log p comes, you know that, okay, uh, you just write this Vg is equals to, okay, P is equals to rho kBt. So you can write Ug, uh, Ug is equals to 1 by rho, this is F, this is del F, this is del sorry del oh sorry del Y, here P R T. Here's rho F. Log is comes del of, sorry. Okay, I will give you. I will print. I will give. I will write this thing and upload this in the drive. Is it okay?
Okay.
Okay. Yes. 1 by rho del del p, this term will come here. 1 by p del del p, this kind of term will be here. So this log p, that thing is written as the log p, but I have to just check. So this equations of how this uh, geostropic velocity vector change with the vertical pressure and or the vertical log space vertical pressure uh, is related to the gradient of temperature and the direction component. One can see that this del t del y at constant p is less than 0 as the case of the mid and the high altitudes of northern hemisphere. Just then by equation 7.26 it can be you can get the 26a, you can get this del ug del ln pz is less than 0. Since the pressure falls with the altitude, this means that del ug del z is greater than 0 in the mid and the high latitude of the northern hemisphere. Thus, these latitudes, as we move upward, this wind accelerates from the west to east direction. Thus, the strong west to east winds are seen to flow. These are known as the westerlies at the high altitudes of northern hemisphere as we move from the equator. The temperature gradient with y is positive. This in the southern hemisphere, but the Coriolis parameter f is negative. So in the southern hemisphere as well, you will get this del ug del ln pz, this I cap component terms to be less than 0. So this del ug del z is greater than 0. Now thus the also in the southern hemisphere there is a westerly wind that which tends from to blow from the west to east direction in the K cap zone. So in the both two direction we get the westerly wind in the mid latitude, high or the mid latitude. Now we will solve few questions with these concept. So in the 58, the first question for today is a northward moving wind in northern hemisphere tilts eastward due to what condition? Pressure gradient only, uh, conservation of angular momentum and Coriolis effect, gravity and the frictional dissipation.
Option D.
Uh, uh, it moves to eastward due to the conservation of angular momentum and the Coriolis effect. It is moving eastward due to conservation of angular momentum and the Coriolis effect. In the question 59, vertical pressure gradient is balanced by gravity. This condition is known as what? Cyclostropic balance, hydrostatic balance, geostropic balance, and the gradient wind balance.
Hydrostatic balance.
Yes, this is known as hydrostatic balance. The horizontal pressure gradient force per unit mass is what? Minus grad P by rho minus G plus grad P by rho and grad phi. This question is option A is correct. Minus grad P by rho is the horizontal, this pressure gradient force per unit mass. The first of this, minus grad P by rho. And question 61, geostropic balance occurs for what? When gravity balance the Coriolis force, pressure gradient balance Coriolis force, friction balance Coriolis force, and the centrifugal force balance pressure gradient.
Option D.
Yes, 61 is option B. The pressure gradient force balances Coriolis force. A part of Coriolis force comes from the centrifugal force and the angular momentum conservation, what we saw in the previous slide. And 62, in the 7.23, the meridional geostropic velocity equation has been given. So this meridional geostropic velocity is proportional to what? 7.23, this equation, in the meridional direction. Meridional direction, that is Vg, that is proportional to del x uv, other the direction. Meridional geostropic velocity is proportional to zonal temperature gradient, zonal pressure gradient, meridional pressure gradient, and the vertical velocity. You can see that this UVG is along the Jacob direction. It is proportional to del P del X direction. That is X directions how the pressure is changing. So for the meridional velocity, it is proportional to the pressure gradient of the zonal. Zonal, yes, I cap. Question 62, option B. And if this is the zonal geostropic velocity, then there will be meridional pressure gradient. And this 63, cyclones rotate counterclockwise in northern hemisphere because the pressure gradient force dominant, Coriolis deflects wind rightward, temperature gradient reverses, and the friction enhances westward flow.
Option B.
Yes, 63 is option B. Coriolis deflects the wind rightward. Now question 65. Surface winds deviate from the geostropic because a stronger Coriolis force, frictional drag, weaker pressure gradient, and the centrifugal acceleration. 65.
Option B. Frictional.
Yes, friction is the main thing for the surface winds deviation. Question 66. Thermal wind relax, horizontal temperature gradient and the vertical shear of geostropic wind, pressure gradient and gravity, frictional force and the Coriolis force, temperature and the humidity gradient.
Please explain this thermal.
Thermal wind, horizontal temperature gradient and a vertical shear of the geostropic wind. So this vertical shear of this geostropic wind arises from this is from the thermal wind equation, and you can see this the how with changing pressure direction this Vg or the geostropic velocity is changing. This part you can consider to be the shear term of the geostropic wind, and this temperature gradient Tp, gradient of Tp, this is the temperature horizontal temperature gradient, and this thermal from the thermal wind equation itself, this thermal wind question comes. So question 66 option A is correct.
Okay.
Yes. You can see the gradient of the geostropic wind with the vertical change of pressure with respect to the horizontal temperature gradient along isopressure contours. This equation main thing. This k cap cross grad p of t is the thing for how the horizontal temperature gradient changes for the isopressure contours. Now,
Grad P means del del P or
yes, del del P of T. Yes. Sorry. Question 67. Is the westerly strengthen with altitude in mid latitude because temperature increases poleward temperature decreases and large meridional gradient. Coriolis is weaker, friction grows stronger.
Option C.
Here the 67 7 is option B is correct. The westerly strengthening effect is due to the temperature
Altitude. Okay, okay,
decrease.
fine. I
Yes,
thought latitude.
and the large meridional gradient presence. Question 67, option B is correct. Now question, I guess 64. Now question 64. Uh, Geostropic velocity is always what direction? Parallel to pressure gradient, opposite to pressure gradient, perpendicular to pressure gradient, and vertical to isobar. Geostropic velocity is always perpendicular to pressure gradient, vertical to isobar, uh, opposite to pressure gradient, and parallel to pressure gradient. We can see this geostropic velocity. This geostropic velocity you can see, this is Vg, is written as the grat p cross k cap cross grat p direction. So you know this cross product formula. So grat p is the on the perpendicular axis of Vg, and also grat phi is also the perpendicular axis of the Vg. Now from this formula you can see that this geostropic velocity is always perpendicular to the pressure gradient, not opposite or parallel.
Okay.
And also the this geostropic velocity Vg you can consider, that is k cap is the cross term, k cap is the your vertical direction, cross gradient of p direction. So it is also perpendicular to k cap direction or the vertical direction. Geostropic velocity always perpendicular to two directions. One is your vertical directions perpendicular, and the cross grat p's directions perpendicular. Now this same slide we discussed the last day. That is about the thermally indirect and thermally direct circulations. So thermally direct circulation occurs when warm air rises and the warm air rises and the cold air sinks, while the thermally indirect circulation occurs when the cold air rises and the hot air or the warm air sinks. Now thermally direct circulation is driven by the difference in the heating. As you can see that in the earth, this equatorial region or this tropical this kind of 23 degree, this up to this region receives the constant heat from the sun always, but this receives less amount of it. This is the cool region you can say. So this thermally direct circulation drives the difference in the heat, drives by the difference in heating, where the warm air rises, cold air sinks, and directly converting thermal energy to the kinetic energy. Now this Hurtley-Cell which is observed in between 0 to 30 degree latitude, that is the and the 90 degree to 60 degree latitude, is the Hurtley-Cell and the Porret-Cell are the primary example of the thermally direct circulation. This process helps to redistribute the heat from the warmer region of the air parcel or the warmer region of the air column to the cooler region of the air column, maintaining the thermal balance in the atmosphere. Now the thermally indirect circulation case is fully opposite, where the cool air rises and the warm air sinks. Means that there must be some external energy supplied by any external means, just like from the atmospheric wave or etc., or rather than pure temperature induced density difference, this process occurs. Classic example is the Ferrel cell, which is observed in between 30 to 60 degree. Despite of the warmer temperature here, it has been seen that the air from the up dips here, but here from the here at the 60 degree warm cooler air rises. So this opposes the thermally direct circulation. Now our atmospheric circulation can be described with the two types of wind pattern. One is the low level wind pattern and another is the high level wind pattern. So this low level wind pattern, for this low level wind pattern, you can say this is our low level wind pattern, or this creates the low level wind pattern. In the subtropical zone, that is up to 30 degrees north to 30 degrees south, the Coriolis parameter is low, because Coriolis parameter has a dependence of the sine phi, and phi is small near 0 degree, or 30 plus 32 minus 30, this zone. Hence the wind flow is primarily dominated by the pressure gradient that is caused by the differential thermal heating. Such circulations are the thermally direct circulation. They arises in the association with differences in surface temperature and therefore low level geopotential gradients or the pressure gradients. Large scale thermally direct circulations are called the Hartley circulations, that covers the full depth of the troposphere in between 30 degree north to 30 degree south. Two of this cell exist. One is the northern Hartley cell and the southern Hartley cell, you can say. And this north Hartley cell, you can say this, here the wind is flowing from this direction. If there was no Coriolis force, this would flow this direction and this direction. So this wind will flow towards the, this will move bend towards the right of its, and this would move towards left of it. So this low level pattern of the Hartley cell contributes to this subtropical zone slow level wind. These winds have two names, that is the northeastern trade wind and the southeastern trade wind. Also for this cell, this polar islands are the same kind of wind. You can see here also 90 degree to 60 degree there will be wind flow, and that flow also will bend. This will bend to the right, and this will bend towards its left. And for the this westerlies, westerlies, you can, this westerlies, here is the thing, there is 30 degree to 60 degree there will be flow, so this will bend this direction, and here also the this to this flow will be, what's the, okay, no, this to this wind flow. This is a low level wind. Yes. They will bend this direction. This two Ferrel cell direction known as the northeast, sorry, Ferrel cells are known as the mid latitude westerlies, and in south, and mid latitude westerlies in the north, south and north, this two. Now we can see such cells Such wind cell can be plotted as a combination of zonally averaged annual mean meridional velocity and the zonally averaged annual mean vertical velocity as seen in this figure in your lecture slide. We can where the contours of the meridional velocity and the vertical velocities are plotted. The warmer surface near the equator is associated with the region of the rising air that results the low pressure zone near the equator at the surface. This air rises up, then flows toward the subtropics, and then this air cools by the time it reaches to 30-degree northern latitude, and most of it descends down to create a subtropical high pressure zones. Then surface level winds flow into the equatorial low pressure zone from the subtropical high pressure zones. This surface level winds, what we saw, are the partially reflected in the right and in the northern hemisphere and left in the southern hemisphere by southern hemisphere, and it causes the trade winds. Now this Coriolis force creating the northeast trade winds in northern hemisphere and the southeast trade winds in the southern hemisphere blow towards the equator from the 30-degree latitude to the 0-degree latitude. This surface level winds meet near a zone that is known as the intertropical convergence zone. The zonally averaged vertical and the meridional velocity can be combined to form what is called the mass stream function contours. Annual mean zonal meridional wind velocity and the vertical pressure velocity has been plotted in this figure. You can see from your lecture slide. The strength of the Hartley circulation will be velocity dependent on the rates which the stream function changes with pressure and the proportional to the gradient of this mass stream function. The mean meridional zonal average vertical velocity depend on the rate at which the stream function changes with the latitude. This stream function contours are plotted with the seasons in the figure besides, along with its annual value.
Excuse me, ma'am.
Yes.
From where they get the velocity for this?
Yes.
It is not theoretical, I suppose.
No.
It is practical.
This velocity are all this velocity has been taken from this. You can just check. Yeah. Here you can say here in the figure this ERA interim is a website which have this velocity informations. So this ERA interim has been this velocity data has been taken at the different latitude station or different phi station since 1979 until today, and it has been taken for the 6-hourly temporal resolution. This is the ERA interim data atmospheric for the atmospheric science.
Okay, ma'am. Thank you.
Okay. Here in this figure you can see when this ERA interim thing. In some figure there is. In the northern hemisphere, Hartley cell is the strongest during the December to February. That is the when there is south hemisphere summer, while the southern hemisphere circulation cell is strongest during the northern summer. This is the one of the key points for us, that when there is a other hemisphere summer, then the other hemisphere summer, then the Hartley circulation becomes the strongest. For the southern summer, the northern hemisphere Hartley cell will be strongest, and for the southern hemisphere summer, the northern hemisphere summer, southern hemisphere Hartley circulation will be strongest. This is because the winter hemisphere has the strongest temperature gradient, and this temperature gradient you saw, this is effectively to the Vg, that has been related to the Vg always. There is an insolation and the effective equator where the insolation is maximum moves to the summer hemisphere. Note that this part of air descending down in the subtropics move towards the pole and contribute to the transport of heat from the low to high latitude. Now other two zones are the subpolar zone and the mid latitude zone. Subpolar zones are the subpolar zone is the 60 to 90 degree, and this are we know the polar regions is extremely cold due to they are not receiving solar insolation as like from the equator. Air near the pole is cooler, so it sinks down towards the surface, creating a polar high pressure zone here. Creating a polar high pressure zone here. On reaching the surface, this cold layer then moves towards the equator or the course towards the lower latitude, and the 60 degree north or 60 degree southern latitude collides with the poleward moving surface collides with the poleward moving surface winds from the subtropical high pressure zone, and it is forced to rise here. It Ferrel cells component, it collides with it, and it forced to rise in the upper direction. Thus the subpolar low pressure belts are generated at the 60 degree north and the 60 degree south. You can see this polar here, the air parcel was sink down from here, sink down, and it was coming towards the equator. But the Ferrel cell, there is a thermally indirect circulation, so here there is some flow towards the 60 degree north or 60 degree south, you can say. And this, when they collide, they tends to rise in the upper direction. So here is always a low pressure belt here at the 60 degree north or 60 degree south. The rising air then moves back towards the pole to create the polar convection cells. The surface level meridional wind is from the poles towards the 60 degree latitude. This meridional wind means surface level meridional wind, that means meridional component, that is the northern south or J cap component of this first figure for today. They are strongly reflected towards the right in the northern hemisphere and left in the southern hemisphere, as the Coriolis force told us, and hence they blow in the east to west direction. Hence the surface level wind in the subpolar region are called the polar slayers. In the mid latitude, that is the 60 degree to 30 degree to 60 degree, this region, a weak convection cell is also exist. This why weak, I will not understand. I could not understand today also. I will see next day in some class. But which is called the Ferrel cell. Part of air rising in the subpolar lows move towards the low latitude and descends towards the surface at 30 degree north or south at the subtropical high pressure zone. However, the air at the 60 degree is considered to be cooler than the 30 degree. Hence, Ferrel cell is thermally indirect. In that, within the Ferrel cell, colder air at 60 degrees rising up and warm in the 30 degree descending in the surface. Hence, pressure gradients are caused by the differential heating is not responsible for the Ferrel cell circulation system. Instead, mass momentum balance constraints due to stronger and the thermally direct Hadley and polar cell results formation of weaker Ferrel cell. The surface level winds blow from the subtropical high to the subpolar low in the meridional direction. Coriolis forces strongly deflect the wind to the right in the northern hemisphere and the southern hemisphere to the left of its going direction. Hence, the surface level winds are primarily blow from the west to east direction, known as the westerlies or the mid latitude westerlies. mid latitude westerlies, and this three cells has been shown here with the clear view. Now you can so due to strong insolation near tropics, the convection cells extend much further up to the vertically near the equator than near the poles, where the air is much colder and denser. Hence, this troposphere boundary, or the troposphere stratosphere boundary decreases from the 15 km and equator to the up to 7 km at poles. Here you can see there is more circulation here, or the cells are more in height, and here cells are lower in height. So this mean three surface winds at the polar stellies, that are 90 degree to 60 degree, and the mid latitude westerlies, that is within.
Excuse me, ma'am.
Yes.
Can you explain why this is 15 or 15 kilometer less than 15 kilometer at the polar? Why height and difference?
Why height or difference? This I cannot explain, I guess.
Okay.
This is one thing. There is some weakness thing has been there given. This weaker ferrule cell. So this weakness, whether this weakness. How long
is after 30 degree north or south, but at the equator it is 15 kilometers.
Yes.
Then it is decreases gradually.
Maybe it is due to the fact that how long air parcel can. If I understand this, this is maybe due to the fact that air parcel how long it can go up and then decrease.
That's why I'm asking how it goes at the equator. It goes, it rises very high altitude.
Yes.
Latitude.
They are saying that this is the stronger insolation. Stronger insolation means more solar in the region where the more solar radiation has been received. There the air parcel has high.
But that means their energy is high. Absorb energy is high.
Yes, that is their absorb energy is high. So they can go up to high altitude. That.
Okay, ma'am. It may be.
In that sense, that is correct, but mathematically there must be some mathematics for how long air parcel can reach. From the insolation idea, that is if you put that more energy to some parcel, it has high tendency to go upward.
Yes, ma'am.
Yes, yes, that thing you can say, but what other factors help here I cannot tell. So there are three kind of surface winds were discussed. The polar stellies, mid latitude westerlies, and the northeast trade winds in the northern and the southern hemisphere. Hemisphere. Now there is another kind of another two slides. Okay. There are two and the upper level or the high level winds are as like below. The structure of the high level winds is shown here in this figure. We have the aloft south westerlies moving from equator to the subtropics in the northern hemisphere, and the aloft northwesterly is moving from equator to the subtropics in the southern hemisphere. You can say these are the top branch of this circulation cell. These are the top branch of the circulation cells, and they will move as the Coriolis force tell them to move. So this wind corresponds to the upper branch of this Hadley circulation system. These two winds, this is the southwesterly wind aloft and the northwesterly wind aloft. They are also there exist the upper branch of the polar cell. You get these two types of wind also. From the subpolar low to the upper branch of this polar cell moves this wind from the subpolar low to polar high. But in this upper branch of this polar cell, the strong Coriolis force is acting. So this Coriolis force deflects them to the fully horizontal direction. So strong Coriolis force at this high latitude, that is greater than 60 degree, strongly deflect these winds to the right in the northern hemisphere and to the left in the southern hemisphere. So this upper branch of this polar cells has direction from this west to east direction and west to east direction, and they are known as the polar westerlies. In the mid latitude, that is within 30 to 60 degree, this convenient there is a phenomena is more nice. In the mid latitude, we have the large meridional gradient in temperature, that is the temperature along the J cap direction. Large meridional gradient in temperature on both land and air columns. Since the feral cells is weaker compared to weaker in the sense you can say it is receiving less amount of solar radiation and is thermally indirect. Thus, del T by del Y is less than very less than 0 in the northern hemisphere, and del T del Y is southern hemisphere, it is greater than 0. You can just check it. That is the in the northern hemisphere, the y direction in the y direction, as you increase your y direction, the temperature is decreasing. So you are getting the del y is less than 0. But in southern hemisphere, as you are as y is along the j cap direction, as you are decreasing y along the j cap direction, temperature is decreasing, so you are getting this positive
Excuse
value.
me, ma'am.
Yes.
A cap direction means towards the pole.
No, this is not k cap. I'm in j cap direction. Yes. You can
J
see
cap.
this. We are saying that del t del y is less than 0 in very less than 0 in the northern hemisphere, and it is very
J cap
less.
is towards the pole.
Yes, towards the pole. So suppose you are moving, you are here and you are going along the j cap direction, that is del t del y. So your temperature is decreasing as you moving along j
But
cap.
in the northern hemisphere, it is written that del T del
Del
Y is
y.
greater than 0.
This is less than 0.
In the northern hemisphere.
Yes. And in the southern hemisphere, you are itself decreasing
Reverse.
k cap,
Okay.
j cap. You are itself decreasing k cap, and also this t is decreasing as you are moving to the southern pole. So this thing can gives you positive value.
J cap direction of J cap is opposite in the southern
Yes,
hemisphere.
j cap is minus j direction when
Yes.
you are moving. Yes, in that sense, the del t del y or del t on the as you are moving south pole is positive. So now you can, in that sense, you can write the equation of UG and the VG, that are the geostropic balance equation in the as the zonal and the meridional component. And using this thermal wind equation, using this thermal wind equation, we see that the large meridional temperature in 7.23 and 7.24 gradients would imply that the winds in the both hemisphere will accelerate to the west to east direction with altitude, that is del u del z is very greater than 0. Hence we observed a strong aloft westerlies blowing on the mid latitude both in the northern and the southern hemisphere. The zonally average wind velocity contours has been shown here. So also the zonal wind is westerly through most of the upper troposphere, that is upper troposphere is 5 to 12 kilometer, and peaks at the speed that in excess 30 meter per second in the subtropical jet stream, which is centered near the 30-degree latitude and at the altitude of about 12 kilometer. This subtropical jet stream, or which is observed to be in the at the 30-degree latitude and the 12 kilometer above the sea level, is strongest in the winter season when the large meridional temperature gradient exists in between warm high altitude winds coming from the equatorial low and the high altitude cold winds coming from the subpolar lows. This zonal winds at the surface at the westerly at most of the latitude in between 30 to 70, but the belt is between 30 degree to northern to 30 degrees south. The zonal easterly surface winds prevail. In the stratosphere, a strong westerly jet is present in the winter, stronger than in the southern hemisphere, stronger in southern hemisphere, and shift easterlies in summer. Thus, in terms of high level wind in the troposphere, we have aloft northwesterly in the northern hemisphere and aloft southwesterly in the southern hemisphere between 0 to 30 degree. Subtropical westerly jet stream at the 12 kilometer, or suppose the higher part of the troposphere at 30 degree to south north to 30 degrees south, where warm winds from the Hartley cell converge with the cold wind from the subpolar lows transported by Ferrel cell. Meet latitude aloft westerlies between 30 degree to 60 degree latitude, which are particularly strong as they are driven by strong meridional gradient temperature. And at last, the polar aloft, which is from the west to east direction, known as the polar aloft westerlies. Here in this figure, the latitude height cross section of zonal average wind speed for different month when there is boreal summer, boreal winter and the boreal summer has been given. That is December, January, February, and June, July, August. Control levels are interval of the 5 meter per second. You can see here here westerlies are plotted in red and the easterlies are plotted in blue. You can see how their velocity is changing with the altitude and the pressure, with the latitude and pressure. Now we will solve few questions from this previous slides. Question 68. In northern hemisphere, we saw that del T del Y is less than 0. Then vertical shear of zonal wind is positive, negative, 0 and depends on friction. Del T del Y is less than 0. We can check. This is given. Del T del Y is less than 0 in the northern hemisphere. The vertical shear of zonal wind. We have the equation of this zonal wind.
Which equation, ma'am?
This 7.26 vertical del T del Y.
Okay, it's negative. Delta delta.
Del T del Y is negative. This is This is negative, yes. Question 69. The subtropical jets is strongest in the winter because friction is lower, meridional temperature gradients are steeper, Coriolis weakens, polar easterlies levers.
Option D.
Yes, the meridional temperature gradient is steeper is the main cause for the subtropical jet to be stronger in winter. And we saw the subtropical jet is the when it is at the 30-degree latitude, at the 30-degree latitude at the 12 kilometer, about 12 kilometer level for the troposphere. Now in 70, in the stratosphere, winds remains westerly year round. Rivers seasonally in between westerlies and easterlies are always easterlies, do not exist.
Option A.
So here they are giving that here this line gives that in stratosphere a strong westerly wind is present in the winter, stronger in the southern hemisphere and shifts to easterlies in the summer. So in the southern, in the stratosphere, winds reverse seasonally between the westerlies and easterlies. In 71, the thermally direct circulation has warm wind rising, cold wind sinking, cold wind rising, warm wind sinking, geostropic balance only, wind only due to friction. Yes, this is option A is correct.
Option A.
Yes. Question 72. Hadley circulation extend roughly in between this is
C.
0 to 30 degree. This has been given. Hadley circulation is strongest in the winter hemisphere where the stronger temperature gradient is seen. Question 73, option B is correct. Question 74. Friction causes winds to blow parallel to isobar directly along the pressure gradient, exactly opposite to the Coriolis force and the opposite pressure gradient. I have not made any slide for the frictional force, but you can answer this. Friction causes
Opposite option C and D, but opposite to Coriolis force.
I guess option B is correct. Directly along the pressure gradient, the friction.
But friction is always acts in the opposite direction.
Opposite direction of movement, I guess. Friction acts.
Yes, ma'am.
But pressure gradient is the low pressure to high pressure. High pressure to low pressure. There will be movement of air. So high pressure to low pressure, there will be movement of air. If friction would act opposite to it. So pressure gradient opposite to Coriolis force. I will. I guess option B is correct. Just move to the next question. I will try to confirm.
Okay, okay.
Question 75. The cyclonic wind spiral inward at surface because friction reduces Coriolis force, gravity dominating, and pressure gradient weakens, centrifugal balance holds. 75, option C is correct. As the pressure gradient weakens at the surfaces, the cyclonic wind spiral inward. Now question 76. Final momentum balance includes pressure gradient force, Coriolis force and friction, pressure gradient force, Coriolis force and friction, only pressure gradient force and the Coriolis force, only gravity and the centrifugal force, and pressure and friction only.
Option A.
Yes, question 76, option A is correct. Pressure gradient force, Coriolis force, and friction. Question 77. Hydrostatic balance applies vertically because friction cancels, Coriolis negligible, gravity is comparable to the vertical pressure gradient force, and the pressure is constant. Hydrostatic balance is option C. Yes, gravitational force is equal to vertical pressure gradient force. And of 78, cyclonic activity is weaker near equator because gravity is stronger, pressure is weaker, Coriolis is zero, friction is absent. Question 78. Coriolis force is stronger, not stronger, or it becomes weaker near the equator because the Coriolis force becomes zero. Question 70. Sorry. Now we have discussed this. This intertropical ITCZ, or this intertropical convergence zone, shifts with latitude of maximum insolation, equatorial ocean current, polar jet movement, and Earth's magnetic field. This ITCZ shifts with what? Latitude of maximum insolation, equatorial ocean current, polar jet movement, and Earth's magnetic field.
Option C.
Question 79, option A is correct. Latitude of maximum insolation up to latitude of maximum insolation, okay. This ITCZ shifts. This ITCZ shift is primarily due to the seasonal movement of the sun's direct overhead position, which causes the zone of maximum solar heating and the low pressure to migrate towards the north in the northern hemisphere, and when there is a boreal summer, and the southern hemisphere when there is a summer, that is the June July JJA. This seasonal shift is influenced by the tilt of Earth's axis, causing the variation of the solar insolation across hemispheres, resulting in the ITCZ following the thermal equator. This positive when there is the northern time summer, it will be towards our 23:30, and in the January this will shift here. You can see one the main thing, that in the this is something closer and there in the land, but this is shift is very high here. You can figure out why this shift varies. Over the differential hitting between northern and the southern hemisphere can cause the asymmetrical shifts in the ITCZ towards the warmer hemisphere. Over land, ITCZ migration is more pronounced than the ocean due to the faster heating and the cooling of the land surfaces than the water. The shifting of ITCZ drives the wet and the dry seasons in the tropical regions and directly affects the monsoonal circulation and tropical cyclone formation. In the recent times, climate change and the regional warming patterns have also influenced the shifts in the ITCZ, causing a regional small variation in this ITCZ. Such as the northern shift over the Indian Ocean and Eastern Africa, and southward shift over the Eastern Pacific and Atlantic Ocean. In summary, ITCZ shift is mainly seasonal and longitudinal migration driven by the sun's insolation, what is received by the earth, and the differential hitting of the hemisphere over the land mass
Excuse
and the,
me.
yes.
Excuse me. It is said the southward shifts over the eastern Pacific and Atlantic. But where is the southern shift?
Southern shift is
Could
this.
it-
This is southern shift. This blue line,
Okay.
and this is northern shift.
So mean is in between.
No,
The original one is the
yes,
original line.
original one should be this, because this two waves
Okay.
should, this two low level winds should meet at zero. This line,
At the equator.
yes, this should be along the zero, but it is not along the zero. It is just going by this, yeah, by this.
Yes, sir.
Yes, and differential hitting of the land mass and the ocean uh, affects this. Now the question 80, the polar easterlies arises because stronger westerlies jet deflect equatorward winds, sinking cold air at the poles and flow equatorward is deflected by Coriolis, frictional drag, gradient with balance only. Polar easterlies arises because
Option D.
this is option D correct. Sinking air at the poles flows equatorward, and it cannot fully flow equatorward. It have to be deflected by Coriolis, a high amount of Coriolis force, high part of Coriolis force. Question 80, option B is correct. Question 81, Ferrel cell exists primarily due to temperature gradient, momentum balance in between Hadley and the polar cells, strong tropical convection, and the surface friction.
Option B, I think.
Option B, yes. The momentum balance between Hadley and the polar cells contribute to the Ferrel cell formation.
That's why it is weaker.
Yes.
Two cells.
But then why polar? Yeah, that thing. Which cell directly transport heat to poleward? Hadley cell, polar cell, and the Ferrel cell.
Polar cell.
Uh,
Towards directly polar cell.
Directly polar cell, I guess this will be the Hadley cell only, but sorry, that is the, so directly here there is a more energy is being transported from the equator, sorry, yes. I have to be confirmed with this answer, I guess. Direct.
Okay.
What this thing direct means. 82 I could not answer. 82. And next 83, Ferrel cell is indirect because the warm air descends and the cold air rises. Yes, this option is correct. 83, option A is correct. 84, tropopause height is constant globally, higher at pole, higher at equator, lower at pole, higher in the winter hemisphere only.
Option C.
Yes, 84, option C is correct. And 85, Main surface winds include polar easterlies, mid latitude westerlies, and trade winds. Trade winds only, westerlies only,
Option
monsoons
A.
only. Yes,
Option
85 option A. Now 86, subtropical jet forms near 30 degree because weak friction, Hartley and the Ferrell convergence at the tropopause, strong polar lows and the monsoon circulations. The subtropical jet formation 86, that is due to the convergence of the Ferrell and the Hartley in the at the 30 degree. At the tropopause, the subtropical jets are formed. Tropopause means 12 to 15 in that range.
Okay.
Now 87, large meridional temperature gradient in mid latitude cause strong westerlies, strong easterlies, vertical motion only, no effect. That is del T del Y is large in mid latitude.
Option A.
Yes, 87 option A is correct. This 87 strong westerlies are formed due to del T del Y's large value at 60 to 30 to 60 this region. Aloft polar winds are easterlies, westerlies, northerly, southerly.
Steadily.
Yes, 88 option A is correct. 89, stratospheric circulation in summer becomes westerly, easterly, mixed and absent. Stratospheric circulation changes direction in the both winter and summer, and it has seen that the stratospheric circulation is easterly when it is summer and westerly it is winter. Question 89
Okay.
option B is correct. Now we should I would just go for another page. Just give me some. Now we will cover some part of this week 8 and then we will go back to week 7 content. Now this
Okay.
era, we had shown that the era interim is the atmospheric reanalysis or atmospheric data source. It has been produced by the European Center for the Medium Range Weather Forecast and it stores the data since 1979 and it has 3D atmospheric field maps, surface fields map, ocean land coupling variables. You can see their website and check what kind of data is available with them. And in the next part, that is the ocean circulation, there are different types of data is plotted here. But how the salinity is varying with depth, how the temperature is varying with depth. That data has been taken from the MIMOC mapping method of climatology website. That is maintained by the specific marine environment laboratory, and this data sets is the global monthly min ocean climatology has been stored, and different variables such as have seen that temperature, salinity, density, those are plotted here. And this ocean heat and the salt barrier study, mixed layer depth variability, those study, and the climate model validation, how or making the model how the atmosphere shapes the oceans circulation, or how they are impacting climate change. In those sense, this MIMOC dataset is useful. Now we will solve this some small questions from or few questions from this week 8 content. So now it is given that in subtropical ocean, salinity is dash at greater depth. Salinity increases, salinity decreases, salinity constant, or salinity has no effect. You can see this figure for your reference. In the subtropical ocean, the salinity
Increases.
increases. Yeah,
Increases.
yes, the salinity increases with the ocean depth. Now, the two most important properties of the ocean that determines the oceanic circulations are pressure and temperature, density and pressure, humidity and salinity, temperature and salinity. The two most important properties in the ocean that determines oceanic circulations are temperature
Temperature
and
and
salinity.
salinity.
Yes, temperature and salinity. Question 3. The depth over which the wind driven surface currents are generated is also called what? Ekman transport, Savudrop, Ekman layer, and Ekman velocity flux. The depth over which wind driven surface currents are generated is called Ekman transport, Savudrop,
Ekman layer.
Ekman layer, Ekman velocity flux. Yes, question 3, Ekman velocity flux is the right answer. Now we will not discuss this today. We will come to this later. Now question 4. Which of the following determines the thermohaline circulation? A wind-driven oceanic circulation that occurs primarily near the coastlines of the continents. A large-scale ocean circulation that is driven by the global wind pattern and the Earth's rotation. A circular pattern in the ocean that is driven by differences in water temperature, salinity, involving the sinking of water, salty water, and the rising warm, less salty water. And option 4 is a small scale ocean current system that primarily affects surface water movement in tropical regions. Which of the following determines or defines the thermohaline circulation? A wind-driven oceanic circulation that occurs primarily near the coastlines of the continent. A large-scale ocean circulation that is driven by the global wind pattern and also determined by the Earth's rotation. A circulation pattern that is defined by the difference in the water temperature and the salinity, the main two properties, involving the sinking of cold salty water and the rising of warm less salty water. And the small scale ocean current system that primarily affects surface water movement in the tropical regions. Question 4 option C is correct. Thermohaline circulation is the circulation which is just like our atmospheric circulation, where warm air parcel was moving up the thermal direct and the cold air parcel was coming down. Here also in the ocean there is that kind of circulation is known as the thermohaline circulation, because there the salt is involved also. Here this is called the sinking of the cold salty water has sinked towards the center of earth, or the so is low direction, and this warm less salty water rises up. Is it?
Excuse me, ma'am.
Yes.
What What are the other options? They are false or correct?
They are false.
Okay.
Yes. Question 4, the thermohaline circulation is just like the thermally direct circulation what we discussed in the atmosphere, but here haline terms is coming because you are taking the salinity you are considering. Now question 5, which of the following describes the Wakat circulation? A large scale atmospheric circulation pattern which involves rising of warm air near the equator and sinking of cold air at the poles. Is it a atmospheric circulation? And a large scale oceanic current that circulates water in between equator and the poles. A large scale oceanic circulation which occurs between the equator and the poles. An atmospheric circulation pattern in the tropics in the meridional direction, or the K cap, the south to north direction, involving the rising warm air near equator and the sinking of cold air near the subtropics, associated with the low level trade winds. And the atmospheric circulation, this is last option, it is an atmospheric circulation pattern in the tropical Pacific Ocean, characterized by the zonal movement of air along the equator, uh, involving the rising of warm air over the West Pacific and sinking of colder air over the Eastern Pacific. This Waker circulation is what type of circulation? Is it an atmospheric circulation or it is a oceanic circulation?
Oceanic, equatorial Pacific Ocean, that is
Question 5,
atmospheric
option D is
pattern.
correct. Yes.
Option D, yes, ma'am.
An atmospheric it is an atmospheric circulation pattern, uh, but it is connected to the ocean cover, we where the tropic it is occurred where the near tropical Pacific Ocean, and characterized by the zonal movement or the east to west to east movement of air along the equator, and involves rising of warm air over the Western Pacific and sinking of colder air over Eastern Pacific. Now it comes to question. Sorry. There are three different layers in the ocean you have seen. The first layer is a thin well-mixed surface layer, which is steered constantly by winds and the waves. So here effectively the temperature and the salinity values are almost constant here. Temperature and the salinity values are almost constant here. You can see here. Now the second layer is the permanent thermocline. Thermocline is a region of the rapid temperature change with depth which lies in below the well-mixed layer up to the depth of 1000 meter or 1 kilometer below the sea level. The temperature gradient here is balanced by the heat transport from the well-mixed layer and the slow upward movement of colder but less saline and hence less dense air water from the below. The temperature at the bottom of this permanent thermocline is in between 4 to 5 degrees Celsius, and in the mid latitude it becomes 0 degree in the mid latitude, and in the 0 degrees Celsius it already reaches 0 degrees Celsius at the pole. So at the 0 degrees Celsius less than 1 kilometer there is always water in its freezing state. The deep layer is almost uniform temperature and salinity that lies below the thermocline up to the ocean bottom. Ocean bottom is taken to be about 7 kilometer on average. In the deep layer, that is within 1000 to 3700 meter, 1000 to 700 meter. 1000 meter to 3700 meter, there is a layer is constant known as uniform layer. This deep layer, this temperature remains relatively uniform and slowly drops from the 4 degrees Celsius to the base of the thermocline 2 degrees Celsius at the ocean bottom. However, at the poles, this bottom is around also 0 degree Celsius, which already rise from the permanent thermocline base. Up to thermocline base to 0, to the most deep, there is the water is in the freezing state in the pole. Now question 6, which of the following describes an equatorial Kelvin wave, a type of radially outward directed oceanic water transport that is caused by the anticyclonic high pressure systems over the subtropical oceans, a type of atmospheric wave that moves poleward from the equator affecting the weather pattern in the mid latitudes associated with the index cycle, a type of oceanic and atmospheric wave that propagates across the equator in the meridional direction, influenced by the Coriolis force and the changing location of the intertropical convergence zone, and is caused by the monsoon system, a large-scale pool of warm water that moves eastward across the equatorial Pacific during El Nino condition, and is typically associated with changes in sea surface temperature and pressure. Now, what describes the equatorial Kelvin wave? So the first option is, it is a type of a radially outward directed oceanic water transport that is caused by the anticyclonic high pressure system over the subtropical ocean. Or is this a type of atmospheric wave that moves poleward from the equator affecting the weather pattern in the mid latitude associated with the index cycle, a type of oceanic and atmospheric wave that propagates across the equator in the meridional direction, influenced by the Coriolis effect and the changing location of the intertropical convergence zone, and is cause of the monsoon system. And last option, a large scale pool of warm water that moves eastward across the equatorial Pacific during the El Nino condition, and is typically associated with change in sea surface temperature and pressure.
A large scale pool of warm water that moves
Yes,
eastward.
question 6 is option D correct. This is a Kelvin wave, is a large scale pool of the warm water across the equatorial Pacific where the during the El Nino condition, and it is associated with mainly the temperature and the pressure. Which of the following defines the ENSO, that is El Nino Southern Oscillation? A regular predictable weather pattern that affects only Atlantic Ocean causing the consistent seasonal change, a climatic phenomena that is characterized by periodic fluctuation in sea surface temperature and atmospheric pressure in the central and the eastern tropical Pacific Ocean, including global weather and climate pattern, a large-scale ocean current that circulates around Antarctica affecting only the southern hemisphere weather, a typical ocean wave that travels across Pacific Ocean, leading to short-term changes in coastal weather patterns. Which of this following defines the El Nino Southern Oscillation? A regular, predictable weather pattern that affects only Atlantic Ocean, causing a consistent seasonal change. A climate phenomena that is characterized by the periodic fluctuation in ocean surface temperature and atmospheric pressure in the central and the eastern tropical Pacific Ocean, including global weather and climate pattern. A large ocean current that circulates around Antarctica affecting only the southern hemisphere weather, a type of ocean wave that travels across the Pacific Ocean, leading to short-term changes in coastal weather pattern.
Option B.
Yes, question 7 option B is correct. It is a climate phenomena which is characterized by the periodic fluctuation what happens in the oceanic surface temperature and the atmospheric pressure in the central or the western Pacific. And this and so is the cause for the global climate and pattern change on the global weather. It is not for the any particular zone. Question 8. A dash is defined as the difference of the sea level atmospheric pressure in between West Pacific on the east and the East Pacific. Southern Oscillation Index, El Nino Southern Oscillation, La Nina, and trade wind. Which of the following is defined to be the difference of the sea level or the sea level atmospheric temperature in between West Pacific and the East Pacific? This is Southern Oscillation Index. 8 is option A is correct. 8 Southern Oscillation Index is the atmospheric pressure difference in between Western Pacific and Eastern Pacific. Now question 9. That dash is markedly more saltier compared to dash. Which of the oceans are more saltier? Atlantic is saltier than Indian Ocean. Atlantic is saltier than the Pacific Ocean. Pacific Ocean is saltier than Atlantic Ocean. Indian Ocean is saltier than the Atlantic Ocean.
Option A.
They are giving 9B a correct answer, but we have need to just check.
Pacific.
Yes, but we need to discuss about this. Discuss. So the Atlantic Ocean is more Pacific salinity saltier than the Pacific Ocean. Now question 10. Identify whether this statement is true or false. Salinity varies with both latitude and depth. This is true and false. Question 10. This is obviously true. Salinity of the ocean has dependence on where you are taking the measurement, at which 5, and at what depth you are taking that measurement. Now describe the seventh group in the oceanography. This is a unit of measurement of ocean salinity, including the amount of salt that is in the 1 cubic meter of seawater. A measure of volume transport of ocean currents equivalent to 1 million cubic meters of water per second. A term which is used to describe the temperature gradient in ocean, indicating the change in temperature with depth. A unit that is used to measure the pressure exerted by ocean currents on the seafloor, expressed in Pascal. This seventh group in oceanography is what? It is a measurement of measure of ocean salinity. Is this a measure of volume transport of ocean current equivalent to 1 million cubic meter of water per second? A term that is used to describe the temperature gradient in the ocean, indicating the change of temperature with depth. A unit that is used to measure the pressure exerted by ocean currents on the seafloor, expressed as pascals. Question 11, option B is correct. Sieve drop is a measure of volume transport of ocean current equivalent to 1 million cubic meter of water per second. Question 11, option B is correct.
Okay, madam. Yes.
Now, question 12. Which of the following explains the Ekman spiral? A vertical column of water in the ocean that rotates clockwise in the northern hemisphere and the counterclockwise in southern hemisphere and caused by the Coriolis effect and the wind driven surface current. A horizontal current pattern in the ocean that causes water to move in the straight line from the equator to poles, driven by differences in water density and temperature. And option C is a phenomena where the oceanic and the atmospheric currents create a spiral pattern due to interaction between wind stress and the Coriolis effect, causing the direction of the wind flow to change with depth. A large scale ocean wave that travels along the equator, affecting sea surface temperature and weather patterns. So, which of the following explains the Ekman spiral? Is it a vertical column of water in the ocean which is rotating the clockwise in northern hemisphere and counterclockwise in southern hemisphere due to the effect of the Coriolis force and the wind driven ocean current? Is this a horizontal current pattern in the ocean that causes the water to move in the straight line from equator to poles, driven by the differences in water and density in water density and temperature? It is a phenomena where the oceanic and the atmospheric currents create spiral patterns due to interaction between wind stress and the Coriolis effect, causing the direction of water flow to change with depth. And option 4, a large scale ocean wave that travels along the equator, affecting the sea surface temperature and the weather pattern.
Option C.
Yes, 12 is option C correct. It is a phenomena where the ocean and the atmospheric currents create a spiral pattern for the interaction between wind stress and the Coriolis effect. And due to Ekman spiral, the direction of the water flow in this Ekman spiral, it is seen that the direction of the water flow changes with depth. Now, question 13. This is a true-false question. A cyclonic and anticyclonic wind circulations tend to cause the net transport of surface waters away from and towards the center of circulation. This statement is true or false? That is, cyclonic wind
True.
tends towards net transport of surface water away from it, and the anticyclonic circulation towards the center of the circulation, it transport the net surface water. Yes, question 13 is true. Now, question 14. In a certain region in the northern hemisphere, away from the equator, that is phi positive in some place, the surface level winds blow in the east to west direction. The Ekman transport of water will be in dash direction. Here we have to check. 14 just live for today. I guess 14 live for today. This we have to check.
Okay.
15, these are AD. Yes, this is okay. Today I am stopping until this. The next questions from the week
Okay.
7, what remained from the week 7 and week 8 content, we will discuss those in the next class. Maybe we will have some extra class in the week after this week. One extra class will be there. We have to just confirm from the NPTEL team. In the middle of this week, we may have an extra class. So I'm stopping the
Okay.
presentation. Okay.
Okay. Thank you. Bye.
Yes. Thank you. Thank you for joining.